So looking at our speakers' publications, you would be excused for thinking that there are two faculty members at Brown University named Brad Marston. One is an eminent condensed matter theorist who's applied sophisticated quantum field theory methods to understanding strongly correlated states of matter, starting with his well-known PhD thesis at Princeton on the large N limit of the Hubbard-Heisenberg models. The other Brad Marston is a climate scientist who's helped found and chaired the American Physical Society topical group on the physics of climate. Much of his research is on the fundamental physics of fluids relevant to climate models. But he's also the co-author of an important early review of fires in the Earth system, which connected outbreaks of fire to climate change. So between them, the Brad Marstons have been recognized with numerous awards, including a Sloan Fellowship, a Fellowship of the American Physical Society, and a National Science Foundation American Competitiveness and Innovation Fellowship. Brad has also served on the APS Board of Directors. Now, one objection that Brad might make to this introduction is that it overstates the separateness of his two scientific lives. And because I think an important part of his message is that the climate is a problem of non-equilibrium statistical physics and is therefore directly connected to condensed matter physics. Today, he's here to tell us about a spectacular way in which the two fields come together. So welcome, Brad. We're delighted to have you here, and the floor is yours.
Thank you very much, Harsh, for that kind introduction. I'm really sorry that I can't visit because I always like meeting people and finding out what they're doing at each place. But I guess this is the next best thing. And as Harsh described, I have a kind of schizophrenic scientific existence. But in the work that I want to describe today, I hope you'll see that they've actually managed to come together in some fashion. So let me share my screen. So I want to tell you about this surprising connection that we found between climate and quantum physics, which I'll call El Nino as a topological insulator. And I hope I'll be able to explain this connection in some regard. So this is work that I began with my French collaborators, Antoine Benaille and Pierre Delplace, both at ENS de Lyon. I began working with them when I went on sabbatical in Lyon, but this project didn't really emerge until a few years later. And then more recently, I've been interested in the application of these ideas to plasmas, gaseous plasmas. And so I've been working with Jeff Parker, who's a young assistant professor at Wisconsin, and Steve Tobias and Zoe Zhu, who is a graduate student at Harvard. So here's the outline of what I want to talk about today. I want to give you a brief introduction to the El Nino and Kelvin waves, which are an important type of wave in the fluid Earth system. And I'll talk about some simulations and observations that kind of illustrate these waves. Then I'm going to talk about broken discrete symmetries in the Earth system, mainly time reversal and parity. I'm going to switch topics and briefly review the quantum Hall effect and topological insulators, some topics that I'm sure that you've heard about in other colloquia and perhaps from Harsh. And then I'll briefly touch on some other classical topological waves that have a connection with the waves that I'm mainly interested in. We'll turn to the kind of mathematical heart of the talk by looking at the shallow water equations. And I'll show you that there is an unexpected or overlooked singularity in the wave solutions of these equations that tells us that there's some non-trivial topology lurking behind the scenes. And that's quantified by something called the Chern number. And then I have a kind of a collection of topics. We'll see how much time I have, but thinking about protection from scattering and some other systems that we're interested in. So please feel free to stop me at any time if you have any questions. Now I want to begin with this quote from the Feynman Lectures in Physics that I think touches on the kind of connection I want to make here. He said, in the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot see that the water flow equations contain such things as the Barber pole structure of turbulence that one sees between rotating cylinders. He's talking about Couette flow here. And today we cannot see whether Schrodinger's equation contains frogs, musical composers, or morality, or whether it does not. So I'm not going to try to touch on morality or even frogs, but I'll try to tell you something about waves and fluids. So this is a satellite reconstruction of the sea surface height in the ocean, in the Pacific Ocean, measured by laser altimetry. And I'm going to set this movie into motion. The main thing to note is that the red represents higher than average sea surface, and blue is lower than average. And the amplitude here is about plus or minus 20 centimeters. And the red it's colored red also not necessarily because it's higher, but it's also because it's warmer, because it's reflecting the fact that the water in that region is warmer than average. And so it's expanded. And this is the reason why there's this bulge here. So this is during a relatively weak El Nino year. And let me set this in motion. It's going to run over 3 months. And you can see this pulse moving across the equatorial Pacific, right on the equator, and it's moving to the east. This is warm water that's surfacing, and when this warm water surfaces off of the coast of South America, then the Earth is in a phase called the El Nino. It's named after the Christ child because it was discovered by Peruvian fishermen over 100 years ago. They noticed around Christmas time, sometimes their catch of fish was greatly reduced. And that we now know is because this pool of warm water off the coast inhibits the upwelling of nutrients that would feed the fish. So they were the first ones to notice that. And here's a cross-sectional view of the same thing, actually, during a stronger El Nino. This is now measuring the temperature directly because it's coming from a vast array of probes, Argo float array, which are floating around the ocean, thousands of them, and they dive down to depth and measure the temperature profile, and then they pop up to the surface and radio by satellite their findings. And this array has greatly increased our understanding of the oceans. So I'll send this into motion, and you can see this cross-section along the equator. We have this warm water that is pooling off of the coast of South America and moving into the El Nino phase. And then the phase eventually reverses, and then we'll see a wave here that is actually propagating the opposite direction. And when we have cooler water coming over the South America and warmer water pooling over the Indonesia area, then we're in the opposite phase that's called the La Nina. So that wave that was going across the equator is called a Kelvin wave. And I want to illustrate it in a simple model, a two-layer model of a fluid. So this is a cross-sectional view again. And so the horizontal direction is either latitude or longitude, and the vertical direction is height. And what we have here is a colder, denser blob of fluid underneath a warmer, less dense fluid. And so this fluid is subjected to the force of gravity, of course, and gravity wants to push this bulge down. So it acts as a restoring force. And that by itself will lead to the propagation of waves at this interface. And so we can do a simulation dropping a rock onto a fluid Earth or fluid planet covered completely with fluid. And this wave pulse will just go out and go to the antipode of the sphere and then pass on through itself and then come back. So this is a sphere right now that is not rotating. And if we do the same thing, if we look at it in cylindrical coordinates, we see much the same thing. So this pulse emanates out, just like a rock dropped into a pond. And now I want to repeat this numerical experiment, but I'm going to turn on the rotation of the Earth. And the rotation of the Earth will have a dramatic effect on this fluid because it introduces the Coriolis force. And the Coriolis force is a new restoring force in the horizontal direction that's now added to the restoring force in the vertical direction due to gravity. So I'll start with exactly the same initial condition, but now this is a rotating planet. And what you see is this non-dispersive wave that's trapped in the equator. It's called, this is the Kelvin. And it will just go around and around this planet. There's some additional waves that are generated from the rock, the initial pulse, but the most coherent part is this Kelvin wave. And so due to the Coriolis force, a fluid parcel that moves north from the equator is going to be deflected to the right and then back to the equator. Similarly, a fluid parcel that if it were moving to the south, it will be deflected back to the equator. So the Coriolis force acts to trap the waves at the equator. Now, there's not just a Kelvin wave, there's another wave. This Kelvin wave has symmetry with respect to the equator. If we reflect about the equator, there's another wave that is anti-symmetric with respect to the equator, and it's called the Yanai wave. And you can see the anti-symmetry here, and you can also see it's dispersive. The phase velocity and the group velocities are different. So you get this kind of phasing as it's moving along. Nevertheless, it's another equatorially trapped wave. And what we're going to see later in this talk is that some basic considerations from topology predict the existence of these two waves. So these simulations were done with a computer program that I wrote, and I put it on the Mac App Store for those who have Macintosh computers. It's free. You're welcome to download it. It allows you to visualize a lot of sort of basic fluid problems on an idealized spherical planet. And I use it for my research, and but it also has it's kind of fun to play with, I think. It's called GCM. So I want to talk about broken symmetries, and I'd like to begin by reminding you about the CPT theorem, which says that the combination of charge conjugation and parity and time reversal leaves the system unchanged. And it's one of the most fundamental ideas, I guess, in theoretical physics. Quantum field theories are generally invariant under CPT. So here I'm not concerned for the moment with charged fluids. So I'm just going to be concerned with parity and time reversal. And so if we think about a planet that's rotating, then it's rotating around its axis. This would be like Earth rotating towards the east. And if we put a mirror up and look at that planet in the mirror, the mirror image will be rotating in the opposite direction. So parity reverses the direction of rotation. And therefore, if a planet has a definite rotation, it breaks parity, the symmetry of parity. They're related by the parity operation, but it is no longer symmetric under the parity. Likewise, if we do time reversal, we run the movie backwards, that will also reverse the direction of rotation. So the combination of P and T leaves the planet invariant. So that's the manifestation of the CPT theorem. We can see that algebraically if we think about the Coriolis force. So the acceleration in a rotating non-inertial reference frame is equal to the normal acceleration you would have if you were in an inertial frame, F over m, the force over the mass. But then there's these two additional terms that involve the cross product of the rotation, angular rotation vector with the velocity in the rotating frame. And then a second term, which we usually neglect in geophysics. It's there too, it's just the centripetal acceleration. So if we, and if we think about the effect of time reversal, then when t goes to minus t, the acceleration is left invariant because there's two time derivatives. And over here, the velocity, though, is changes sign on reversal if things are moving back. So if omega is fixed, then this term would effectively change sign on reversal symmetry. So the rotation of the breaks time reversal symmetry, much like a magnetic field breaks time reversal symmetry. Now, most of the fluid motion in the atmosphere or oceans is in the horizontal direction. And so the component of the Coriolis force that we're interested in is the components that are in the horizontal direction, which means that what we want to do is find the local normal component of the rotation vector. So if we're at some latitude here, maybe we're at Case Western, we look upwards, this is our unit radial direction. We take the projection of omega in that direction. That gives us 2 omega times the cosine here of the co-latitude. So it's maximal at the north and south poles, maximal in magnitude, but it changes sign across the equator. So the Coriolis force changes sign across the equator, and we can think of the two hemispheres of the Earth as breaking time reversal symmetry in opposite senses because this Coriolis parameter F changes sign, which is manifest in the fact that, for example, a high pressure region in the northern hemisphere circulates in a clockwise way, but in the southern hemisphere, it would be in a counterclockwise direction. And we use the symbol F here because this is the same factor that appears in the Foucault pendulum when you're working out what the precession rate of the Foucault pendulum is. It depends on the latitude, so you can use it to measure your latitude. Okay, so now I want to switch gears briefly and talk about some quantum physics, and namely the well-known quantum Hall effect, which was has been recognized by a number of Nobel Prizes, but most recently in 2016, the role of topology in physics was recognized. And I want to focus on the contributions of David Thales, who provided a topological explanation for the quantization of the Hall resistivity or conductivity, and explained why it's such a robust phenomenon. So here we see this Hall resistance as a function of applied magnetic field, and we have these well-known plateaus, which are so precisely quantized that they're now used as a standard of electrical resistance. There's David Thales. So a mechanistic understanding of this can be provided by just thinking about a semi-classical picture of electrons spiraling in cyclotron orbits in a semiconductor with the magnetic field lines here perpendicular to this surface. So they're spiraling around, but at the edges of the surface, because the circles don't complete, they form semicircles, and the electron is dragged forward in one direction only. So manifestation of the broken time reversal symmetry. On the other side, it's going the opposite direction. And that means that if there's some impurities or obstacles here, because the electrons are only going one way, those obstacles have less effect, and it's hard for them to backscatter. And this gives a kind of a mechanistic understanding of why we get these robust plateaus, but it's somewhat unsatisfying because it doesn't explain why they have these particular numerical values, for instance. So that's where Thales came in and gave a topological explanation, which I'm not going to repeat here, but we're going to touch on exactly the same physics in the fluid context. But before I leave the quantum realm, let me just remind you of the more recent a more recent manifestation of topology in quantum physics, quantum matter, which is topological insulators, which are here compared schematically, contrasted with the quantum Hall effect that we just discussed. And roughly speaking, you can just think of it this way, that there's both spins of the both electrons of both spins are participating, and spin up is going one way and spin down is going the other way. They're coupled, the spins are coupled to the motion by the spin orbit interaction, which is strong for the heavier elements. And therefore, under time reversal symmetry, this is actually symmetric, because if we reverse the direction of motion, we also reverse the direction of the spin, and the blue and red states are just interchanged back to the same system. So this is just to say that topology can arise in situations where there isn't a broken time reversal symmetry. Yeah, we see there's some similarities with the broken time reversal case. And one of the nice advantages of these materials is that their energy scales are relatively high, unlike the quantum Hall effect. And so it's possible to look directly at the dispersion of the electron states using angle-resolved photo emission. And here we see we have red spin up electrons going to the right, the blue spin down electrons going to the left. And so these states are dispersing in energy wave number space in opposite directions. They have opposite slopes, and that they cross these edge modes, cross through this otherwise forbidden region, the insulating region, the region that would be otherwise lighting. And this is sort of the amazing thing about the topological insulators, is that we have these, although they're insulating in the bulk, there are these edge modes that are conducting. And the dispersion has been directly imaged now many times by angle resolved photo emission spectra, and out comes this nice dispersion. All right, so now with that, I'd like to return to equatorial waves and show you some results that were known from the 1960s by directly solving the wave equation, the linearized wave equation, in the presence of both the gravity, the buoyancy force that I discussed, and the Coriolis force. And so this was the dispersion relation. And Matsuno in 1966 first found it by solving the wave equation. And in fact, it is kind of an interesting calculation, leads to Hermite polynomials. So it's rather similar to Schrodinger equation calculations that physicists are very familiar with. And there's 4 branches to the dispersion relation. First of all, there are these gravity waves. Those are the waves that in the absence of rotation we saw. Those were the waves that were propagating out on the sphere just due to the buoyancy force. But the dispersion relation has been altered by the presence of the Coriolis force. The gravity waves are non-dispersive in the absence of rotation, but they become dispersive with rotation. And there's a gap, a frequency gap, to excite them due to the rotation. Then there are what are called planetary waves. These are lower frequency waves. These are the waves that at the mid latitudes, where you're located, bring the weather systems every few days. The high and low pressure zones, the frontal systems, these are all from planetary waves, or also known as Rossby waves. But then there are these two unusual waves. So the planetary waves and gravity waves are in these families, but there's this solitary or isolated Unai wave and the Kelvin wave. So the geophysicists knew about these waves as a direct solution of the wave equation, but they found them kind of mysterious. What was their origin? And when we submitted our paper to Science, we got a number of referee reports, and one referee wrote this: the question of why the equator supports a unidirectional wave, the Kelvin wave, is interesting scientifically and important mathematically. I have asked the question myself and have been unsatisfied with my own answer, as well as the answer of other scientists. So there was a feeling there was something mysterious about these waves. Some deeper explanation was missing. So before I give you that deeper explanation, I want to spend a little bit of time telling you some of the manifestations of the El Nino, of which the Kelvin wave is an important component of. So the El Nino oscillation, what we usually call the ENSO oscillation, El Nino Southern Oscillation, is the largest climate oscillation that occurs on human scales. And it's the one that's responsible for lots of the wiggles that we see in the global temperature. Global temperature is going up due to global warming, but there are these oscillations. And the biggest contributor to those oscillations is the El Nino. So the El Nino is a coupled phenomena. It couples the atmosphere and the ocean. And during the El Nino, when it's a warm pool of water off of South America, that tends to stimulate convection in the equatorial regions because the warm water is evaporating, and that leads to cloud formation, and that will tend to cause the atmosphere to change its direction of circulation along the equator in the east-west direction, this thing called the Walker cell, from the neutral condition, where instead the convection is concentrated more on the western side of the Pacific. And so this change in the atmosphere has far-reaching ramifications clear across the planet. But before I mention that, we can use those clouds, the fact that the clouds track where the warm pool is, the warm pool of water, to study the brightness of the Pacific as a function of wave number and frequency, and thereby indirectly back out the dispersion relation of the Kelvin wave and the Unai wave. And that's been done in this work by Claudis et al. And you can see from the power spectrum, here we have wave number versus frequency, that their Kelvin wave is quite apparent. This is the symmetric contribution, symmetric across the equator. The anti-symmetric part shows the Unai wave. And then there's some other interesting excitations, this one called the Madden-Julian oscillation, which I may have time to talk about later. So the clouds actually give us a way to see more directly these Kelvin waves. So as I mentioned, the Kelvin wave, the El Nino has far-reaching ramifications for the Earth's climate. These connections we call teleconnections, that is, they're connections at a distance. So one thing that happens as far as North America is concerned is that during the El Nino phase, we tend to get more rain in California and relatively less rain in the Pacific Northwest, whereas in the La Nina phase, which is what we're in right now, the reverse tends to hold. It's not 100% correlation because there's other oscillations going on in the climate system, but it's a fairly strong correlation. So here's a view from Valentine's Day in 2019, so two years ago, when we were in a El Nino phase, and there was a very strong flow of moisture going into Southern California. This is called an atmospheric river, and it caused widespread flooding and washing out in the mountains of California due to this atmospheric river. Here's just obviously a satellite view of that. This is something I've been interested in for a long time. When I was a graduate student, I noticed that these fluctuations in the temperature of the Earth from year to year have a strong correlation with the change in the amount of carbon dioxide in the atmosphere. Of course, the atmosphere carbon dioxide is increasing because of our input, and it also oscillates from season to season as plants grow and die back. But removing those two regular features still shows a whole bunch of other oscillations in the amount of carbon dioxide in the atmosphere. And I found that there's a strong correlation between equatorial temperatures and carbon dioxide concentration, which at the time we didn't really understand. We speculated on what possible connections are, but there's been a lot more work since then. So I'm going to tell you about how this connects to the El Nino. Let me mention, though, that at the time that we finished this work in the late 80s, this is how much data we had. The carbon dioxide concentrations have been measured by Charles Keeling starting in the 1958, but this correlation has continued. And so if you look all the way up to the present, there's a strong correlation between the temperature and the carbon dioxide. So we now know that during the El Nino phase of the climate, there are these effects on the equatorial climate, namely that the Amazon basin tends to be drier than average, and so that decreases photosynthesis that would absorb carbon dioxide. The equatorial regions of Africa and sub-Saharan Africa tend to be hotter than normal. That increases decomposition of organic material, releasing carbon to the atmosphere. And then there tend to be more fires in Indonesia. And so all three of these things add carbon to the atmosphere. And an example of a positive feedback process where the warmer Earth adds more carbon to the atmosphere than would otherwise be there. In this case, is just triggered by the natural El Nino cycle.
Just to get an idea of scale, how does this compare to, say, anthropogenic carbon?
So it's kind of comparable. The amplitude is kind of comparable to a yearly input of carbon dioxide from humans, but because this reverses, as the plants start growing back, it will absorb it. Over the long term, the human input vastly exceeds it. So on the other hand, there's the question that if the Earth is warming, as the Earth warms, then we would expect that there could be some additional carbon added over the long term from these various processes. This is a view of the Pacific from a La Nina year. This is, I think, from 2018, if I remember right. Here you see an atmospheric river going all the way from the warm pool, now located on the western side of the Pacific, across the Pacific to giving water into the Pacific Northwest. And if you look carefully, you can see this smoke coming from the fire. This was the year that there were these terrible fires in Northern California that killed quite a few people because California was in a drought in this year. So it's kind of amazing how connected the climate system is. Now I want to talk about some other wave systems briefly. So this comes from an experiment that has been done at Chicago and William Irvine's group. And what we're looking up at a bunch of gyroscopes that are suspended from the ceiling. Each one of these white circles is a small gyroscope that's going to be set into motion in the same direction. And they're coupled together by little permanent magnets so that if you jiggle one, it creates a wave excitation. And so what the Irvine group did is they made all these gyroscopes rotate the same way so that they tend to precess in the Earth's gravitational field in the same direction, and they break time reversal symmetry. And then they gave the system a little jiggle. And what we'll see, the amplitude is indicated by the colors, is that a wave propagates around the edge of the system. And it's very much the same as our equatorial waves, where we have a boundary. In the case of the Earth, there's a boundary between the two hemispheres that break time reversal symmetry in opposite sense. In this case, it's just a boundary between one system that breaks time reversal symmetry in the same way and the vacuum, or the absence of any matter. So now I want to turn to the mathematical heart of this theory, which is not very hard to understand, and be able to understand it completely right here. So I first need to tell you about the shallow water equations, which are the equations that give us the waves. The shallow means that I'm going to be looking at waves that have a wavelength that's long compared to the depth of the water. So in the case of the ocean, its average depth is about 5 kilometers, but those waves that we saw, the Kelvin waves, they had wavelengths on the order of thousands of kilometers. So this is a good approximation. So the fluid is characterized by some height as a function of the horizontal directions, some height, and also a velocity in the horizontal direction, which I'll call u. It has two components, an x and a y component. And the shallow water equations are here. So the first equation says that the time rate of change of this height is governed by the divergence of the fluid. If the fluid is moving out from, say, this bulge, if it's moving out, then the fluid, because it's conserved, is going to go down. So this first equation is nothing but the conservation of mass. The second equation is basically F equals ma. It says that the acceleration has two components. One is due to gravity. If there's a gradient in the height here, then this bulge wants to push out. And so it will accelerate the fluid as the bulge goes down. And then there's the Coriolis force that's moving at right angles. So we have the cross product between the vertical and the two components of the velocity. There's also this term. This is a nonlinear term, which I'm going to neglect because I'm going to study the equations in their low amplitude. But the origin of this equation is the fact that what we have over here is what's known as the material derivative or the covariant derivative. It just says that what we're really interested in is the acceleration of a parcel of fluid. Imagine putting some dye in the fluid and to label that little region. We want to understand how it accelerates. So it's the F equals ma applies to that material that's actually being moved. And so we have a kind of total derivative here that is standard in fluid mechanics. And it's this nonlinearity that leads to much of the richness that we see in the world around us, which, however, I'm going to neglect it here. So the first thing we do is we non-dimensionalize these equations to remove the dimensions. And we can do that by noticing that there's a speed, which is the square root of the gravitational constant acceleration times the average height of the fluid, which I'll call capital H. So that's the speed that the gravity waves emanate from. And then there's a length scale, which is the speed divided by the 2 times rate of our local rotation rate of our planet. And so that allows us to get rid of some of these factors. And let me introduce capital H, this average height of the fluid. And then we can non-dimensionalize the velocity with respect to the speed, c, and time, and the Coriolis parameter, all of these things. And we're left with a set of very simple partial differential equations that tells us something about how the height of the fluid and the x and y components of the velocity vary. And here's the Coriolis force, this kind of renormalized Coriolis force. And if you like, you can put this in the form of a Schrodinger-like equation, because we have a time derivative over here, and then we have some spatial derivatives. If we put i's in front of those look like momentum operators. If we have an I in front of the time derivative, then that looks like the usual Schrodinger. And so this linear operator H, which just has these derivatives or this Coriolis force in it, it turns out to be Hermitian. And so we're on very familiar grounds for analyzing that three-component partial differential equation. If we solve numerically that equation on a doubly periodic plane, so it's periodic in the x and y directions, and we allow the Coriolis parameter to change sign twice as a function of y, we have to let it change sign twice because this is a periodic system, it's not the sphere. Then we get two equators, and this is sometimes called a planet with two equators. It's nice in the sense that it doesn't have any curvature, right? It's just a plane with this periodicity condition. So it's a little bit easier to analyze mathematically than the sphere. And what we see here is now we have a Unit wave and a Kelvin wave dispersing to the right. Here's frequency versus wave number. And we have another one dispersing to the left. Those are waves that are separately trapped at these two different equators. The equators have opposite orientation because the Coriolis parameter is changing from positive to negative when one and negative to positive the other. So this just confirms our understanding and shows that these equations have the content that we want. We're using a nice open source PDE solver called Daedalus that's written in Python that we use for a lot of our work for fluid simulations. So now I want to discuss the essential idea of this topological theory, and that is we're going to go to a region of the planet that's actually away from the equator. So here we are at Case Western, and we're going to ignore the curvature of the Earth. We'll treat this surface as locally flat, and we're actually going to make it periodic in both directions because I want to eliminate any boundaries. I want it just to be as featureless as possible. And we're going to look at the wave amplitudes at that point as a function of wave number. And so we can look at those wave amplitudes as a function of the wave numbers in the x and y direction, kx and ky, and as a function of the latitude. So the Coriolis parameter reaches its maximum value at the North Pole, or its negative maximum value at the South Pole, vanishes at the equator. But we're just going to be fixed at this one particular latitude, and we're going to diagonalize the wave equation here. Because we've chosen it to be completely flat, it's just plane waves. So we can solve that PDE just by substituting in plane waves. And we're going to find that there's some interesting structure to these amplitudes that is going to tell us that there must be something going on at the equator. This is what's known as the bulk edge correspondence. Non-trivial topology away from the boundary tells us something about the existence of waves at the boundary. And it's the same theme that Thales used in the quantum Hall theory and has been used over and over again in this topological wave physics. So topology turns complicated problems into simple ones. It means that we don't have to solve that PDE with a varying Coriolis parameter F, as Matsuno did in the 1960s. So the topology is going to appear when we look at the wave amplitudes in just a moment, kind of a singularity. And it's a singularity that we can't get rid of. And it's very similar to the Hedgehog Theorem, or what's known here in North America as the Hairy Ball Theorem. So if you imagine a hedgehog that is completely, imagine a spherical hedgehog, which has quills in all directions, and you want to comb these quills flat, then you're going to find that it's impossible. There's going to be a problem. There's going to be a bald spot, or there's going to be a kind of cowlick where they stand up on the surface of the sphere. So when I was on sabbatical in France, we were renting a house, and in the backyard there were all these leaves, and I was raking the leaves up because it was the fall. And underneath the leaves was a hedgehog that had gone into hibernation. And because we don't have hedgehogs in North America, so I didn't know what to do. But it turns out that there's a British society on the web that's dedicated to saving hedgehogs. So I consulted them, wrote them, and I got some good advice about how to rebury my hedgehog under leaves. So I like to think that these hedgehogs were sending me an early signal to pay attention to topology. I was a little bit too dense at the moment to think about that, but they came back into my life a couple of years later. So in our case, we're going to see a phase singularity in our waves that is like the singularities in the quills of the hedgehog we won't be able to get rid of. So here's our plane, XY plane, horizontal plane at Case Western, and we're going to diagonalize it with our plane waves. And we're going to get some very simple dispersion relation, which has some nice symmetries that have to do with the fact that the fluid amplitudes, unlike in quantum mechanics, the fluid amplitudes are completely real. They are, after all, directly observable. And this is what the dispersion looks like. There's a completely flat band, what we call a zero mode. And this just corresponds to fluid that's moving in a circular motion like those cyclotron orbits that's balanced against the pressure force. This is essentially the high and low pressure regions. And because it's moving in a circular motion, it has zero frequency. Then there are true waves that are oscillating up and down as a function of X and Y. And these are these Poincare gravity waves that we saw previously in the dispersion relation. And I've colored these dispersion relations by something that is a measure of the topology, which is a Berry's phase that is going to change sign as we move from the southern hemisphere to the northern hemisphere. And this gives us a kind of way to understand that bulk boundary correspondence, because if you think about continuity, that the topology of this negative frequency solution should match on to the positive frequency solution as we pass through the equator. That suggests that there should be a wave that passes through this otherwise forbidden region in frequency space, and those are the Kelvin and Unit waves.
So, Brad, I just had a quick question.
So now it's,
I guess you do have a conjugation. I mean, like you said, charge conjugation. This is a neutral fluid, but you do have a charge conjugation symmetry here.
Right. Yeah. Under complex conjugation. It isn't a real charge. It's just the reality condition here.
Right.
Yeah. I'll talk about a charge fluid in a bit.
Right. But it does produce that reflection symmetry in the spectrum as well as the zero mode.
Right. That's right. It has to have this reflection symmetry just because the real valuedness of the velocity fields. So here's our Schrodinger equation now in K space with our plane wave equation. And all we have to do is diagonalize this 3x3 matrix. That's what it all ends up being. And here's the positive one of the positive frequency solutions. There's also a zero frequency and negative frequency, but it suffices just to look at the positive frequency. It has a kind of interesting structure. It has some interesting phase dependence here. And what we can see, though, is that as we take the wave number k to be smaller and smaller, as we look at longer and longer wavelengths, then there's a singularity here in the phase, because here we have kx over k. This just goes to a constant. Here we have ky over k with an I. And so the phase will wind around by 2 pi rapidly as we approach the origin in k space. And we can make that even clearer if we parameterize kx, ky, and f, our Coriolis parameter on that sphere that I showed you using spherical coordinates. Then we see that we have this cosine phi, the azimuthal angle in this parameter space of wave numbers, minus I cosine theta, that's involving the latitude sine phi. So it's basically cosine phi plus or minus I sine phi. There's e to the I phi is lurking behind this. And the two hemispheres, the solutions in the northern summer hemisphere can be, we can make a gauge transformation. So wave functions are only defined up to an overall phase. So we can push this singularity around. We can't get rid of it. That's just like the hedgehog. We can move where the location of this phase singularity around. We could eliminate it in the southern hemisphere, but then we end up doubling it in the northern hemisphere. So many physicists have encountered this already in the physics of the Dirac monopole, which, if you recall, the Dirac imagined a magnetic monopole as the termination of a semi-infinite solenoid. So the solenoid has all these field lines coming in, and the solenoid ends and the field lines spew out in all directions. And if we think about the Arnaud-Bohm phase of an electron in the vicinity of this monopole, well, if it goes around the solenoid, it's going to feel the flux passing through the loop that's formed by the path of the electron. And so because the wave function has to be single valued, then Dirac argued that meant that the flux passing through had to be quantized. So that led to a relationship between the strength of the magnetic monopole and electron charge, quantizing the strength of the magnetic monopole. But that flux, that solenoid could have come in from any direction, because its only role is to provide a source of this magnetic field where it terminates. So we can move the solenoid around, and so we can eliminate the singularity where the wave function is, say in the southern hemisphere, and move it to the northern hemisphere. But we can't get rid of it altogether. It's always going to be there. And so it's in the same sense that we have this singularity in the shallow water equations that hadn't been noticed before. This is quantified by some mathematics. We can introduce some gauge connection, and we calculate the difference of the Chern number between the two hemispheres. But basically, all it is it's counting the strength of the singularity. And we can see that there's a singularity of plus 2 pi in the northern hemisphere and minus 2 pi in the southern hemisphere. So the total strength is 4 pi. This is normalized with respect to 2 pi. And so the Chern number, that quantifies this, is equal to 2 at the end of the day. And that tells us from the bulk boundary correspondence that there should be 2 waves at the equator, and those waves are the Kelvin wave and the Unit wave. So that's the logic of the construction of the topology. It's topology in K space, not in real space. So it's a little bit more abstract than we're used to when we're thinking about donuts versus balls. But it's just happening in K space, and that tells us about the existence of these waves. All right, well, I'm almost out of time, so I'm going to skip ahead just a little bit to tell you quickly about some work that we've been doing with plasmas. In a plasma, gaseous plasma, we have a magnetic field, so it's a little bit more like the quantum Hall effect. But that magnetic field has the same in the Lorentz force that it exerts on, say, electrons in a plasma. It has the same cross-product structure that we saw with the Coriolis force. And so if we solve for Maxwell's equations in the presence of a plasma, and we'll be thinking mainly about the electrons here, then it turns out that we can predict the existence of a new wave that propagates in the forbidden region between the plasma excitations and the cyclotron excitations that would otherwise characterize or exhaust the waves in this plasma system. So this wave exists at the edge of the plasma where it's dropping, its density is dropping off to zero into a vacuum. And we predict for the first time the existence of this wave. And we're hoping to do an experiment at UCLA's basic plasma science facility, which you just saw a picture of a device called the Large Plasma Device. We have a couple weeks of time on this machine to look for waves which had never been seen before. So unlike the Kelvin and Unit wave, here we're making a prediction of a new wave. Unfortunately, the experiment has been delayed because of COVID, but maybe sometime later this year, we'll be able to go out there and generate these waves with a microwave oscillator. Well, we also have considered more complicated plasmas that involve the ion motion, such as are found in tokamaks in fusion reactors. There's a type of wave that had previously been identified called a Revere-Shear Alfvén eigenmode. It involves waves that exist in a region where the magnetic field direction is changing, which happens naturally in a tokamak. And we believe that these have an explanation that lies in topology. There's a question. Please go ahead. Sadish.
Oh, sorry, maybe I can ask it later. It's just okay, fine.
Okay. All right, I'm almost finished. Anyone recognize what this is? Yeah.
Feynman lectures.
Yeah, so Feynman's last Blackboard that Caltech saved after he died. It says, what I cannot create, I do not understand. Know how to solve every problem that's been solved, which is pretty ambitious. But he still has over here to learn the Bethe-Ansatz problem, which was kind of interesting since Hans Bethe was a mentor of Feynman's, and the Bethe-Ansatz, I think, dates from 1926. He has the Kondo effect, which he's checked off, I guess. Two-dimensional Hall effect, which was, this is in 1988. So this is pretty current. So he's interested in the Hall effect. I think this is acceleration temperature. This might be the Unruh effect, but I'm not sure. And then he has nonlinear classical hydrodynamics. So I like to think that Feynman would be pleased by this connection that we've made between the Hall effect and at least linear classical hydrodynamics. We still don't know how to really deal with nonlinearities, and that's an active area of research, how to extend our topological analysis to nonlinear fluid mechanics. So, so I hope that my talk has shown that there's some place for physicists to make contributions to our understanding of the climate system. And I'd like to argue that this is badly needed. So there are a lot of great scientists working on the climate system, but I would like to see more physicists join them. It's a very complicated system, so it's not the sort of thing that a physicist is just going to clean up, but they can join with the other scientists that are already working on the problem, many of whom are actually self-identify as physicists, but who are not found in traditional physics departments. This article in Nature, Physicists, Your Planet Needs You, is a similar call for physicists to contribute. And I'd like to invite young physicists especially to think about the climate's problem. As Harsh mentioned, there's a relatively young topical group on the physics of climate in the American Physical Society that I've been part of. It's one of its main missions is to encourage physicists to think about the climate system. They have a great newsletter, probably the best of any of the APS units, sometimes publishes original research. And so I want to invite you to check that out. This was a informal poll that was done right before COVID at some of the APS meetings. This is the one at the March meeting, and where members were invited to rate the importance of these different issues. And you can see that in this case, research funding and climate change were about equal. A detailed analysis of this data actually shows that climate change has a few more dots than research funding, which is amazing. And this has been true at several other APS meetings. So we know that physicists are concerned rightfully about climate change. And so I think this is a good time to start thinking about how physics can weigh in and maybe increase our understanding of the climate system and climate change. So thank you very much.
Great. Well, thank you, Pat. That was wonderful. So let's go straight to questions. And I think Sudesh has a question. Do you want to ask your question now?
Oh, yeah. So I have actually two kind of interrelated questions. The first one is like, in this problem, the nonlinear term was ignored, right? So how important is that? Like, will that kind of add to something?
Right. So the nonlinear term, let's try to, I'm going to try to get out of this. Okay, yeah, the nonlinear term we don't really know how to deal with. So that's a great open question. The nonlinear physics is extremely important in the climate system. And although a lot of our understanding of the climate system comes from the linear waves, such as Rossby waves. So we have, we're just beginning to think about how to study that. If I increase the amplitude of my waves in my simulation, because it includes nonlinearities, and I'm not sure where I have that. Is that here? Yeah. So let me just, I'll just quickly run this. Then, so if I have I'm generating here a Kelvin wave, and it's going to, I have it hitting a region where the water is shallower. And so it's going to slow down and the wave amplitude will increase. And so that increases the nonlinearities. So in this case, amplitude was quite low, so it didn't distort things very much. But if you look at these other two waves down here, and maybe I'll speed it up. I'll speed this one up a little bit. The amplitude is created the initial wave of a much higher amplitude. And so when it goes into this region where it's slowed down, you can see now it's distorting due to this nonlinearity. You're getting a wave breaking effect. And so this is a physics that doesn't have a clear quantum analog. And it would be very nice to understand how to merge our topological analysis with the nonlinearities. So if you have any ideas, I'd be happy to talk to you about that.
Actually, I had in past worked on fluid dynamics, and it seems like oh yeah, we kind of found some symmetries in the nonlinear term and the other terms that were there. Maybe I can share the source here. I mean the paper that we published. Yeah, this one. So that like so it has like symmetries like which couples the Fourier modes with like different modes. I guess I cannot just explain it here. Yeah, so it depends on the wave vectors, like and it kind of has some. Oh, just a second.
Well, I'll take a look at it, and maybe we could talk about this later on.
Oh yeah. Okay.
Yeah, I think that's a good idea. Maybe not should try to do it in real time, but it looks interesting. Arvind, shall we go to your question? Oh, I'm sorry, Sudesh, did you have something else you wanted to say, or?
So I think like maybe that can, I mean, the approximation that you made later on for a square thing, I think that was somewhere later on. Like in that, I guess the equations are of similar form, so that may be useful there. The periodic approximation, I think you mentioned like at somewhere far from the equator.
Mm-hmm. Right. So, yeah, we make this periodic region just for the purpose of eliminating any boundaries, because we want to study the bulk. So this is a common technique for us. Because if we had any boundaries, then we would get more waves, topological waves just produced by the boundaries, and we want to keep it as simple as possible.
Yeah. Okay, thank you.
So Arvind, do you want to go next? Arvind, do you want to ask a question now? Oh, I think possibly we don't have him. Well, while we're waiting for him to come back in, are there other questions?
Brad, this is a wonderful talk. And I just wanted to, I'm scraping some rust off, where years ago I studied nonlinear waves and the layers on the ocean, you know, the Benjamin Ono equation with the solitons, the solitary waves. And
yes.
You've learned so much about, you know, the interaction of linear waves. I just, you know, I'm dying to know you do know, or there are some nice studies where we do have a good feeling for the solitary waves in layers. And I just thought, oh gosh, I'd love to see how this would be connected, because you've got the layers, you've got the waves, you've got the topology.
Right. Yeah. So a thought that we've had was that since these waves are quasi one-dimensional, they're channeled by the waveguide produced by the equator, then it'd be natural to try to include some interactions to produce solitons. And so maybe that would be a route to understanding the interplay between the nonlinearities and topology. So I think that would be an exciting area to explore. I haven't done that yet, and I think there are people who maybe you from your work would be you know, have much more experience with soliton physics. It'd be quite interesting to think about that.
Yeah, very, very stimulating. Thank you. Great talk.
Thanks.
So this might be a good place to transition to having a private discussion. I think we'll close the formal proceedings. So thank you very much, Brad. And I'm afraid that Zoom doesn't allow us to show our appreciation adequately, but that was a great talk. And
thanks, Tarsh. It was a pleasure.